So we'll kick off. Hi everyone. My name is Kevin Latz. This is Kira Loftus. We're network software engineers out of Intel in Shannon, which is hidden away in the west of Ireland. Today we're going to mix some Kool-Aids and hope things go quicker in the internet then. So most of you probably know what DPDK and AF XDP are. For those of you who don't, we'll do a quick introduction. So DPDK is a set of user space libraries and drivers. They aim to accelerate packet processing workloads, and they run on a variety of CPU architectures. Some important things to remember for this talk is that DPDK supports many different PMDs. They're usually device specific, and DPDK has its own memory management system. AF XDP is a kernel-based address family optimized for high performance packet processing. AF XDP has its own sockets in order to move packets from kernel space to user space, and it uses the in-kernel fast path, so it bypasses the network stack in order to move those packets quickly. So if we take a closer look at a simplified diagram of the traditional DPDK model, down the bottom in kernel space we have DPDK-specific kernel modules. They interact with the NICs and expose them to user space. In user space, then we have all of our DPDK PMDs and our applications, and they work together in order to do whatever wonderful things you want to do with your packets. The aim of this work was to introduce and use the new DPDK AF XDP PMD, and then that will directly talk to your NIC driver, so you can still use all of your usual kernel tools that you like using, like ifconfig and so on. So the goal of this work was to have all DPDK applications working out of the box with the new AF XDP PMD. And of course, it should do so with good performance. The performance we were aiming for was close to or on par with the kernel sample app XDP sock. The challenge with this was that frameworks like DPDK have their own memory management, as said. These come with constraints and assumptions of their own. DPDK specifically, we have a discrepancy between the DPDK and AF XDP buffer alignment. So this prevents us from mapping DPDK memory buffers directly to AF XDP UMEMs. And in order to do this mapping, we needed to do some extra work and complexity, which negatively impacts performance.
Okay, so I'm going to talk about how both AF XDP and DPDK lay out their memory for packet handling. I'll talk about the differences between the two and why those differences pose the integration challenges, which Kevin just touched on there. So AF XDP, it's got this concept of a UMEM, or user memory, and it's essentially an area of memory allocated by the user for packet data. The UMEM, it's split up into equal-sized chunks, with each chunk being used to hold data from a particular packet. And how it's used is, for instance, on the receive path, the kernel will place packet data into a chunk for the user space process to retrieve. And in our case, our user space process is DPDK. And on the transmit path, the user space process places packet data into a chunk for the kernel NIC driver to transmit. And prior to kernel 5.4, this UMEM, this area of memory that AF XDP uses to hold packet data, it had a number of restrictions on it in terms of its size and its alignment. The first being that the start address of the UMEM had to be page size aligned, so that's going to be 4K in most cases. The chunks within the UMEM, they had to be power of 2 sized, and kind of as a side effect of that, the chunks could not cross page boundaries. And in a kind of networking use case, that leaves you really with only 2 potential chunk size options, either 2K or 4K. Anything bigger than 4K, and you're going to cross the page boundary, and anything smaller than 2K isn't big enough for a networking packet or networking use case. So in this example here, we've got a chunk size of 2K. We've two 2K chunks per 4K page. And as you can see, none of the chunks are crossing the page boundaries, everything is nice and neat and tidy. The reason for these restrictions is essentially it just makes calculations in the kernel a little bit easier. When everything is nicely aligned, you can use things like masks, etc. Okay, so let's see how DPDK lays out its memory for packet handling and see if it satisfies the requirements of the AF XDP UMEM. So DPDK, as many of you know, we're in the SDN room. It holds packet data inside structures known as memory buffers, or MBUFs for short. And a group of those together is known as an MBUF pool. And DPDK MBUF pools, they don't have as strict restrictions on them as the AF XDP UMEM. So for instance, MBUFs can be of any size within reason, and they can have arbitrary alignment relevant to the page size, so they can cross page boundaries. So in this example here, we've got a MBUF size of maybe 3.5K, and our MBUFs are crossing page boundaries all over the place. And I suppose, why do we care whether or not the DPDK MBUF pool satisfies the requirements of the AF XDP UMEM? And the reason is that in order to get the highest performing integration of AF XDP and DPDK, we need to map the MBUF pool directly into the UMEM to get a zero copy data path, which is obviously going to be the most performant. But as you can see here, that's not possible at the moment. This is just one example of a DPDK MBUF pool. There's plenty more examples of different sized MBUFs, different alignments, and most of them won't comply with the kind of restrictions of the UMEM. But to get around this, the clever folks in the DPDK community have come up with a number of solutions to get them to integrate and work together. Each of them have a varying degree of success in terms of performance. So the first solution that was considered was copy mode. And in this mode, we allocate memory for our UMEM, and we also allocate our DPDK MBUF pool as normal. And we simply mem copy between the two locations in memory. This works really well, but in terms of performance, it's not the most performant just due to the cycle cost of the mem copy being pretty high. But nevertheless, it made it into a DPDK release 1905 as part of the series that initially introduced AF XDP support. The second approach then that was looked into was this alignment API. So it was proposed to introduce a new API into DPDK, which allowed you to kind of specify the type of alignment you wanted for your MBUF pool. And then any application you wanted to work with AF XDP could use this new API and kind of mold its MBUF pool to fit the UMEM requirements. Then you could do the one-to-one mapping and you could get your zero copy performance. But even though this did give really, really good performance, it was deemed a bit too invasive. So it didn't make it into a DPDK release. It was invasive because you had to change your application to get it to work, which kind of went against what Kevin said at the start about apps needing to work out of the box. So that didn't get into a DPDK release, but it generated a good discussion on the mailing list, which led to this third approach. I think it was suggested by Oliver Matz and implemented by Xiaolong Ye. And this approach uses DPDK's external MBUF feature, which allows DPDK MBUF to, instead of holding the packet data in the structure itself, to point to a different location in memory. In this case, we'll be pointing to our UMEM chunk. And then you can achieve your zero copy. However, there are still kind of additional cycles with this solution. So there's additional complexity involved in attaching and detaching that external piece of memory from your MBUF. But then again, it does give a really, really good improvement over copy mode, I think 29% for a certain use case. So it made it into DPDK 1908 as kind of a first gen AF XDP zero copy solution. At this point, we kind of felt that the community had taken DPDK as far as it could in terms of performance with AF XDP. But we still felt that there was still some performance left on the table, some cycles to save. So at that point, we decided it would be a good idea to start looking at the kernel side of things and maybe looking at adapting the UMEM to make it a bit more flexible to work with the flexibility of DPDK, as opposed to trying to make DPDK fit the narrow restrictions of the UMEM.
So what do we do in the kernel when we finally took off our DPDK hats? We took a look at the original UMEM and its constraints, being chunk size aligned, or page size aligned, sorry, was one major restriction that we had to lift. So we enabled arbitrary chunk alignment, so you can now align your chunks anywhere you want within the UMEM. As a part of this, we allowed arbitrary chunk sizing as well. So now you can size and align wherever you want within the UMEM, much more flexible than the original. With this, we also had to allow the crossing of page boundaries, so we now need to keep track of whether pages are physically contiguous in memory or not. If they aren't contiguous, like chunk 3 in this case, let's assume page 3 is non-contiguous to page 2, then it will cross into a non-contiguous memory region, so we can't use that address. We discard it, get a new one, and we use the start of the next page. So we do have a gap in memory. This is just one of the side effects to this kind of added flexibility. But a lot of the time you're going to be a lot more better off with this. With this, we also needed to change the AF XDP RX and TX descriptor. One of the fields within this descriptor is the address field. This is simply an offset into the UMEM of where your chunk is placed. As the packet travels through the data path, various offsets are added onto this. In the original design of this, the offsets were added directly to the address field, so the value would change as it made its way through the data path. At the end of it, when we recycled the buffer, we could simply mask back to 2K, 4K, whatever your alignment was, because it was a power of 2. This isn't possible anymore without doing complex calculations, seeing as we have arbitrary sizing and alignment. So we moved to a model where we took the upper 16 bits of the address field and stored the offset there rather than adding it to the address field. And we kept the lower 48 bits purely for the original base address, or the original offset as it was. This still gives us 256 terabytes of address space, so we've more than enough for now. And what this enables us to do is basically just, when we're doing the buffer recycling, just mask off the upper 16 bits, we have our original address, and we're back to where we were. All of this added flexibility makes the UMEM a lot more flexible, so we can map directly into it, and it really gives us a much more seamless integration with existing frameworks such as DPDK.
Okay, so as Kevin said, now that we've relaxed our UMEM alignment constraints, we can now map our DPDK MBUF pools, no matter what size they are, directly into the UMEM. So using our example from earlier with our 3.5K MBUF, we can size our UMEM chunk to match that, or whatever the MBUF size is, and we can get our seamless zero copy, and we don't need to modify our existing DPDK applications. They're going to work out of the box. So those were our kind of two key goals that we outlined at the start of this, and they were our key goals at the start of this work. So we've achieved those, and in achieving those, we've got both a performant and portable solution. In terms of performance, this solution, it gives a 60% improvement on the copy mode, the first one that I showed earlier, and a further 24% upon the first generation zero copy, which was in 1908, which used the external MBUF feature. So it's a pretty significant performance improvement. And the feature itself, it's available in DPDK 1911, which is the most recent DPDK release. So provided you have kernel 5.4, this feature will be available. If you don't, DPDK will simply fall back to copy mode. I think we're out of time. So, yeah. Okay, yeah. So just a quick note before we end. A lot of people kind of ask, what is the value of integrating AF XDP into DPDK? So DPDK, as many of you know, it provides an application developer with a wide variety of functionality for an application. So things like memory and power management, crypto, virtual networking, QoS, the list goes on. AF XDP then provides unrivaled flexibility, and Magnus touched on this in his presentation first thing this morning. So in contrast with the typical DPDK usage model, or NIC remains bound to the kernel driver, so we can avail of the kernel control paths and have use of our familiar tools like ifconfig, ethtool, etc. So that has a huge impact on the usability of an application and a solution as a whole. So together, essentially, the best of both worlds can be enjoyed, and we can get applications that are high-performing, portable, fully featured, accelerated, insert buzzword here. Yeah, so I think they're just a good combination together. And then just to close, a couple of words of thanks to some people that helped myself and Kevin along the way with this work. Magnus and Bjorn on the kernel side, Bruce, Chi and Zhaolong on the DPDK side, and the DPDK and kernel communities as a whole. Yeah, that's it from myself and Kevin. Yeah, cool. So it really depends on the workload. Off the top of my head, I don't have a number. It really does depend on the workload. Like if it's a heavy workload, they could be pretty close. If it's something like test PMD or L2 forward, there's going to be a bigger delta. I'm trying to think, I think we might have some data published soon, We're running some benchmarks at the moment, so that should be public soon enough.